In this video, we'll continue to look at motion. We'll look at displacement and we'll look at displacement time graphs. We will define displacement, talk a little bit about displacement being a vector quantity, and of course we will analyze displacement time graphs to determine certain information from these graphs. So let's look at displacement. Now, the displacement of a body is defined as the distance moved in a specified direction, right? So displacement can be defined as the distance moved in a specified direction. Right? Now, displacement is a vector quantity and as a result, it may be positive or negative depending on the direction from some reference point, right? So displacement being a vector quantity may be treated as being positive or negative depending on the direction from some reference point. So it may be positive or negative depending on the direction from some reference point. Right? Now, displacement may also be defined as the straight line distance from some reference point. Right? So displacement may also be defined as the straight line distance from some reference point. Symbols, the common symbols for displacement: S, and in some books you may see an X, right? So S or X, and of course the SI unit of displacement is the meter, symbol M. All right, so that's basically what we look at displacement. Now let's talk about displacement time graphs. So displacement time graphs. So displacement time graphs. Now what exactly is a displacement time graph? A displacement time graph is basically a graph which shows our body's displacement changes with time. All right? So a displacement time graph is a graph which shows how a body's displacement varies or changes with time. Right? So displacement on the vertical or the y-axis is plotted against time on the horizontal or the x-axis. Right? Now, what information can we tell from a displacement time graph? We can examine the gradient of the graph. The gradient of the displacement time graph, we'll just write S/T, displacement time graph, gives velocity. Right? So the gradient of the displacement time graph gives velocity. And later on, of course, we'll analyze these graphs to determine if the velocity is increasing, decreasing, or whether it is constant. Right? Now, from a displacement time graph, we can also tell the direction of a body relative to its reference point, right? So we can also tell the direction of a body relative to some reference point based on the actual value of the displacement, but in terms of numerical information, we can use the gradient of the graph to determine the velocity of the body. So let's examine a few displacement time graphs. So on this axis, you have the displacement typically in meters, and on the x-axis, we have the time typically in seconds. All right? So we look at a few graphs. First one, let's just make it a horizontal line. Let's call that graph 1, right? Graph 2 is a straight sloping line, and graph 3 is another straight sloping line, but this time of steeper slope or of a steeper gradient, right? Graph 4 will be a curve. So let's start with graph 4. So at the beginning, it's going to be flat, then it starts to get steeper, there's a straight line segment, then it starts to curve again. At the top, it's basically flat, then it starts to curve downwards, there's another straight line segment, and curve once again. So let's call this point O. Let's call this point A. B, and at the top where it is flat, that point is C, right? Let's call this D, E, and F, right? Now, because it's a displacement time graph, and as I said, that displacement may be positive or negative depending on direction from some reference point, we'll of course extend the graph to include a negative portion. So if we extend the graph, let's say we extend the graph like this. Right, and let's add some additional letters. So this is F, let this be G, this be H, this be I, J, K, and L. Good. So we'll examine our displacement time graphs like that. Right. Now let's examine these graphs. Let's look at graph 1. Now, from our information, we said that the gradient of the displacement time graph gives the body's velocity. So if we want to basically analyze the motion whose graph is shown, the first thing we must ask ourselves is how is the gradient of the particular section of the graph, or how is the gradient of the graph changing? Now, if you examine the graph in 1, it is basically a horizontal line. So we see that basically at time t equals 0, there is some displacement, and as time increases or as time changes, the displacement does not change. So the displacement remains constant, and therefore this tells us that the graph is, or the body is not moving. So if we examine it in terms of the gradient, we can see that the gradient is equal to 0, because of course it is a horizontal line. So the gradient is equal to 0, which of course implies that the velocity is equal to 0. And this is basically the graph of a stationary body. So the body is stationary. right? So the displacement is not changing with respect to time, and this basically means that the body is not moving, it is stationary. Let's look at graph 2. Now graph 2 is a straight line with a uniform or constant slope. So if we examine the graph, we see that the displacement increases steadily with time, and so the gradient is uniform or constant. So the displacement increases uniformly or steadily with time, and this means that the gradient is uniform, and of course it is also positive. And this therefore tells us that the velocity is uniform and also positive, right? So for graph 2, the displacement increases steadily with time. We say the gradient is uniform and also positive, and this means that the velocity is uniform and positive. Now let's look at graph 3. Now, similar to graph 2, the displacement increases steadily with time, and so we say the gradient is also uniform and positive. But if you examine the two graphs carefully, we see that the graph in 3 is steeper than that in 2. So the gradient is greater, the graph is steeper, and so therefore this graph will be moving with a constant but higher velocity than that in part 2. So we say that, well, the gradient is also uniform and positive. So gradient is uniform and positive, but of course greater than that of graph 2, right? And therefore this means that the body moves, or this body whose graph is shown moves with a higher or a larger uniform velocity, right? A uniform velocity, which is also positive, right? So again, comparing these two, we see that the graph in 3, it is steeper. It basically, the displacement will increase more rapidly with time, and so therefore the gradient is larger, and therefore the velocity is greater and also positive. So again, if graph 2 shows a body moving with a uniform positive velocity, then graph 3 shows a body also moving with a uniform positive velocity, but a larger magnitude, right? Good. So having examined those 3 graphs, we will then of course examine the curve, right? And just as before, we'll basically analyze the gradient, and we'll be able to use that to tell what is happening to the body's velocity and so on. Now, before we start to analyze, let me explain the different segments of this graph. Now, at O, the graph is flat, the curve is flat, and it starts a curve between O and A. So in other words, the gradient will start to get steeper, right? So there's an increase in gradient along OA. Now, AB is a straight line segment, and so the gradient, of course, will be uniform. Beyond B, it starts to curve once more and starts to get flatter. At C, the curve is flattened once more, and then it starts to curve downwards, so the gradient will start to decrease. DE is a straight line segment, and beyond D, it starts to curve once more, and at F, once again, the curve is flat, right? And basically, this repeats itself, but below the x-axis. So we'll analyze this graph. So we say at O, the curve is flat. So the curve is flat, which means the gradient is equal to 0. And since the gradient is equal to 0, this further implies the velocity is equal to 0. And if velocity is 0, that means the body is at rest. Right? So at O, the body is at rest. Now, OA, the graph starts to curve upwards. And so the gradient is positive and increasing. So gradient is positive and increasing. And since, of course, the gradient of a displacement time graph gives velocity, then this therefore means that the velocity is positive and increasing. Right? Now, because the body's velocity is positive and increasing, then this means that basically the body is accelerating. So essentially, for OA, we can basically say that the body accelerates uniformly from rest. So the body accelerates uniformly from rest, and this would be in a direction that we consider to be positive. So accelerating uniformly from rest in a direction that we consider to be positive. So in a positive direction. Right? Now, AB, as mentioned before, AB is a straight line segment. And because it's a straight line and sloping upwards, basically the displacement increases uniformly with time, similar to graphs 2 and 3. And this therefore means that the velocity is uniform and still positive, right? So AB, once again, it is a straight line, so that means the gradient is uniform and positive, and this therefore means that the velocity is uniform and positive. All right, let's look at BC. Now if you examine BC, once again it starts a curve, and the graph is starting to become flat, right? So this means that the gradient is decreasing, but it is still positive, right? So the curve is beginning to flatten a bit, and so the gradient is decreasing, but it is still positive, right? So we say that the gradient is decreasing and positive, and this therefore means that the body's velocity is decreasing and positive, right? So BC basically shows that the gradient is decreasing and positive, but of course that means that the velocity is decreasing and positive. Now at C, the curve or the graph is flat. If we were to draw a tangent to the curve at C, it would be a horizontal line, it would be parallel to the graph in 1 and also the x-axis. So at C, the graph is flat, which means the gradient is 0. So the graph is flat, so the gradient is equal to 0. And this of course means that the velocity is equal to 0. Alright? So at C, the graph is flat, the gradient is equal to 0, which means that the body's velocity is equal to 0. And because the body's velocity is equal to 0, that means the body has come to rest. But if you examine the graph carefully, realize that it doesn't stay flat for a long time. So it doesn't remain stationary for long. So therefore we say that the body has momentarily come to rest, or the body is at rest momentarily, right? So at C, the body is momentarily at rest. Now let's examine what happens beyond C, right? And this is where it may start to get a little bit tricky, right? So we know that basically at C, the body is momentarily at rest. Now if a body is at rest, then it can only increase in speed from rest. Its speed can only increase from rest, right? It cannot decrease. However, remember that velocity is a vector quantity, and as such it has both magnitude and direction. And whenever we speak about a negative velocity, it doesn't mean the velocity is actually less than zero. It basically means that the body's speed is, the body has a certain speed, but it is now moving in a direction that we consider to be negative, and so on. All right? So let's examine what is happening beyond C. So CD. So at C, the gradient is equal to 0. We say that the velocity is equal to 0 and the body is momentarily at rest, right? Now CD, the graph once again begins to curve, right? So that means that the gradient is increasing and negative. So the gradient of this graph is now increasing, but it is negative. And this therefore means that the body's velocity, the velocity is increasing and negative. So CD shows the body, shows a portion of the graph where the body's velocity is increasing, but it is negative, right? Now, as I said before, at C, the body was momentarily at rest. So it once again, it starts to move. So its speed is going to be increasing because the speed can only increase from rest. It can't decrease. But this time now, the body is now going in a direction that we consider to be negative. And so it now has basically changed directions, right? So the gradient is increasing and negative, and the velocity is increasing and negative. So basically we say that the body's speed is increasing in a direction which is considered to be negative, right? So the body's speed increases in a direction considered to be negative. Right? So basically what this means is that from O to C, the body was moving in a particular direction relative to some reference point. It stops momentarily at C, and if you notice, beyond C, the displacement is now decreasing. It is going back to 0. And that can only be the case if the body is now moving back towards its initial reference point, right? So basically, beyond C, the body is now moving back towards its initial reference point, right? DE, gradient is uniform and negative, and this therefore means that the velocity is uniform and negative, right? So the body is now moving with a uniform speed, but in a direction we consider to be negative. The body basically is now heading back towards its reference point, right? So DE, the body is heading back towards its reference point, but with a constant speed. Now EF, the gradient will start to decrease, because if you notice, the curve will start to get flattened once more. So the curve starts to flatten, and therefore it means the gradient is decreasing. So gradient is negative and decreasing, right? And this means that the velocity is negative and decreasing, right? So basically what this means is that the body is moving in a direction that we consider to be negative. but it is actually slowing down in that direction. So the body is now moving back towards its reference point, and it is slowing down. And basically at F, it is momentarily at rest. Right? So at F, the curve is once again flat. The gradient is equal to 0, and it therefore means that the body is momentarily at rest. Now let's examine the points O and F. At O, the displacement is equal to 0. At F, the displacement is once again equal to 0. And this basically means that O and F correspond to the same point, which is the starting or reference point. Right? So, the body starts at O, and between O and C, it is moving in a certain direction, away from the reference point. At C, it stops, and it basically reverses direction and begins to move back towards the reference point, and eventually returns to the reference point on F. So basically, O and F correspond to the same physical location, which is the point from which the body initially started moving, right? So at F, the body has returned to its initial starting point. So at F, the body is momentarily at rest and has returned to its starting point, or its starting point. Right? Good. Now, if you were to examine what's happening below here, then essentially what we have is more or less the, how do I put this? Almost the same thing as was happening from before. But the only difference is that for the piece that is above, the displacement, of course, is either 0 or positive, which means that basically the body was at some position relative to some starting point, right? Between F and L, the displacement basically gets very negative, then it goes back to 0, which means now that the body is in the opposite direction of the starting point. What exactly does this mean? Let's say this is our reference point O. For the region where the body's displacement is, say, positive or positive, increasing, and then comes back, that means that the body is to the right of the reference point, right? So O, A, B, C, right? It was moving away from the reference point, and eventually it was basically to the right. But it basically moved away from the reference point, and then it returned to the reference point at F. So basically, for the bulk of this graph, the body was, say, to the right of the reference point. Now down here, where the displacement is basically negative for most part, then the body will be to the left of the reference point before returning to the reference point at L, right? So because we basically analyze similar portions of the graph, we will do the same, but we will not do it in such great detail as we would have before. So let's look at FG. All right, so FG. So we said that basically at F, the graph is flat, so the gradient is equal to 0, which means the velocity is momentarily 0, and the body is momentarily at rest at F. Now, what we will recognize is that what we've analyzed before will be very similar to these portions, so we'll just change the letters and change information accordingly, right? So let's look at FG. Now, FG, the gradient is negative and increasing. So with FG, so let me just remove these letters. So FG, the gradient is negative and increasing, and therefore this means that the velocity is negative and increasing. right? So the body accelerates uniformly from rest in a negative direction, right? So as I mentioned before, the body is now basically at a particular position relative to the reference point. So if for the positive displacement, it was to the right of the reference point O, for the negative displacement, it is basically to the left of the reference point O, right? So that's FG. Now, GH is supposed to be a straight line. The graph might not show it, but it's supposed to be a straight line, right? So GH is a straight line segment. All right, so GH is a straight line. And so therefore, for GH, the gradient is, of course, uniform and negative, which means that the velocity is uniform and negative. So basically, this means that the body's speed is constant while it is moving in what is considered to be a negative direction, right? Now, for HI, the gradient is still negative, but it is decreasing. So the gradient is still negative, but decreasing. And what this basically means is that the velocity is still negative, but it is decreasing, right? So the gradient is decreasing and negative. So that's GH. No, HI rather, HI. HI, the gradient is negative and decreasing, which means the velocity is negative and decreasing, right? Yeah. Now, at I, the graph is once again flat, which basically means that the gradient is equal to 0. So the gradient is equal to 0, and of course the gradient represents the velocity, and so therefore the velocity is 0. So at I, the graph is once again momentarily at rest, right? So the graph is momentarily at rest. Now notice that the displacement is still negative, so therefore it means that the body is some point to the left of the reference point if we consider to the right as being positive, right? So if to the right of the reference point is positive, because the displacement is negative, that means the body is some direction to the left of the reference point. Good? So at I, the gradient is equal to 0 and the body is momentarily at rest. Now IJ, the gradient of course now will start to increase, and the gradient of course is positive and increasing. So the gradient is increasing and positive. So change the sign. Gradient is increasing and positive, right? And therefore that means the velocity is increasing and positive, right? So the gradient is increasing and positive, and therefore this means that the body's velocity is increasing and positive. Now we know that basically that any change in a body's velocity is an acceleration. So therefore it means that basically between I and J, where the gradient is actually increasing and positive, the velocity is increasing and positive, and therefore for IG, then that means the body is accelerating. So the body's acceleration is actually positive, right? Now let's examine JK. So JK, but of course because we're talking about changing the information here, so this is for IJ. The gradient is increasing and positive, and therefore the velocity is increasing and positive, and the speed increases in a direction considered to be positive, right? So in terms of now our reference points, so if we say this is our reference point O, at I, the body is basically stationary to the left of the reference point, and then now it is going to move back towards O, going towards the initial starting point, and we therefore consider that to be a positive direction. It is basically moving to the right, right? Now JK, so JK, the gradient is uniform and positive. So the gradient is uniform and positive, which means that the velocity is uniform and positive, right? So what this basically means is that the body is of course moving with a constant speed back towards O, right? Now with that is JK, KL, the graph starts to curve once more, right? So it goes from being a straight line to a curve, whose slope is decreasing, and so that the gradient is positive. So it is positive but decreasing because it is getting flatter, and so the velocity is positive and decreasing, right? So the gradient is positive and decreasing, but of course it means the velocity is also positive and decreasing. So the positive basically because of the direction, and of course it is slowing down, and hence it is decreasing. Now basically now at L, the body is momentarily at rest because of course the graph is now flat once more, the gradient is equal to 0, and therefore the velocity is equal to 0, and so basically the body is momentarily at rest because the gradient is equal to 0. But if you notice now, it is now again on the x-axis, which means the displacement is once again is equal to 0, and the body has returned to its starting point.